Ground fault circuit interrupter, or GFCI, does not provide ground fault protection when installed without a ground connection. GFCIs operate by comparing the current flowing through the hot and neutral wires of an electrical circuit. The device is designed to detect any difference in current between these two wires, which would indicate that current is leaking out of the intended circuit path. This leakage is known as a ground fault. When a ground fault occurs, the current may be flowing through an unintended path, such as a person's body, which could result in an electrical shock. The GFCI is designed to quickly interrupt the circuit when a ground fault is detected, thus preventing or minimizing the severity of electrical shocks. The purpose of a ground wire in an electrical system is to provide a safe path for fault current to return to the source. This path allows the fault current to quickly trip a circuit breaker or blow a fuse, de-energizing the circuits and preventing a dangerous buildup of voltage. A properly grounded system also helps to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Without a ground connection, a GFCI receptacle can still function as a circuit interrupter under certain conditions. Specifically, it can detect imbalances between the hot and neutral wires, which can occur when current is leaking to ground through a person or object. However, without a ground connection, the GFCI cannot provide the same level of protection as it would with a proper ground. This is because the ground wire provides a low impedance path for fault current to flow, which allows the GFCI to trip more quickly and reliably. If a GFCI is installed in an ungrounded outlet, it will still trip if it detects a significant imbalance between the hot and neutral wires. This can provide some level of protection against electrical shock. However, the GFCI may not trip as quickly or reliably as it would if it were properly grounded. In addition, an ungrounded GFCI may be more susceptible to nuisance tripping, which can be inconvenient. The National Electrical Code, or NEC, addresses the use of GFCIs in ungrounded circuits. The NEC permits the installation of GFCI receptacles in ungrounded outlets under certain conditions. Specifically, the GFCI receptacle must be marked No Equipment Ground and must be installed with a label that indicates that there is no equipment ground. The NEC also requires that the ungrounded circuit be protected by a GFCI circuit breaker. It is important to note that the NEC permits the use of GFCIs in ungrounded circuits only as a temporary measure or in situations where it is not feasible to install a ground wire. The NEC strongly recommends that all electrical outlets be properly grounded whenever possible. If you have ungrounded outlets in your home, it is important to consult with a qualified electrician to determine the best course of action. The electrician can assess your electrical system and determine whether it is feasible to install a ground wire. If it is not feasible to install a ground wire, the electrician can recommend other safety measures, such as installing GFCI receptacles or GFCI circuit breakers. When a GFCI trips, it is important to determine the cause of the trip before resetting the device. If the trip was caused by a ground fault, it is important to identify and correct the source of the fault before restoring power to the circuit. Ground faults can be caused by a variety of factors such as damaged wiring, faulty appliances, or moisture. If you are unable to identify or correct the cause of the trip, you should consult with a qualified electrician. It is also important to test GFCIs regularly to ensure that they are functioning properly. GFCIs should be tested at least once a month by pressing the test button on the receptacle. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. GFCIs are an important safety device that can help to protect you and your family from electrical shock. By understanding how GFCIs work and following the recommendations of the NEC, you can help to ensure that your electrical system is safe and reliable. In summary, a GFCI receptacle does not provide the same level of protection when installed without a ground connection as it does with a proper ground. While it can still detect imbalances between the hot and neutral wires and trip the circuit in some cases, it may not trip as quickly or reliably. The NEC permits the use of GFCIs in ungrounded circuits under certain conditions, but it strongly recommends that all electrical outlets be properly grounded whenever possible. If you have ungrounded outlets in your home, it is important to consult with a qualified electrician to determine the best course of action. An electrician can provide insights on the specific context and ensure safety. The essential function of a GFCI is to protect people from dangerous electrical shocks. It achieves this by constantly monitoring the balance of electrical current flowing in a circuit. The GFCI contains a sensor that detects any difference in current between the outgoing hot wire and the returning neutral wire. In a properly functioning circuit, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. However, if there is a ground fault, some of the current will leak out of the circuit and flow to ground. This leakage creates an imbalance between the hot and neutral wires, which the GFCI detects. When the GFCI detects a ground fault, it quickly interrupts the flow of electricity in the circuit. This interruption happens within milliseconds, which is fast enough to prevent serious injury or death from electrical shock. The GFCI works by opening a switch that cuts off power to the circuit. This switch is typically a mechanical device that is activated by an electronic circuit. The electronic circuit is designed to be very sensitive to changes in current, so it can detect even small ground faults. The amount of current that is required to trip a GFCI is typically very small, around 5 milliamps. This means that the GFCI can detect ground faults that are too small to be felt by a person. The GFCI is designed to protect people from electrical shock, but it does not protect equipment from damage. Ground faults can damage electrical equipment, such as appliances and power tools. To protect equipment from damage, it is important to use a surge protector. A surge protector is a device that protects electrical equipment from voltage spikes. Voltage spikes can be caused by lightning strikes, power outages, and other electrical disturbances. A surge protector works by diverting excess voltage away from the equipment and into the ground. Grounding is a critical safety feature in electrical systems. It provides a low resistance path for fault current to flow back to the source, which helps to trip circuit breakers or fuses quickly and safely. This prevents dangerous voltage buildup and reduces the risk of electrical shock or fire. The grounding system consists of a grounding electrode, such as a ground rod or metal water pipe, that is connected to the electrical panel. The grounding electrode provides a direct connection to the earth, which helps to dissipate fault current. The grounding system also includes a grounding conductor, which is a wire that connects the metal parts of electrical equipment to the grounding electrode. This helps to ensure that all metal parts of the equipment are at the same potential, which reduces the risk of electrical shock. Grounding is essential for the proper operation of GFCIs. When a ground fault occurs, the fault current flows through the grounding system back to the source. This causes the GFCI to trip, which interrupts the flow of electricity and prevents electrical shock. Without a proper grounding system, the GFCI may not trip quickly enough to prevent serious injury or death. There are two main types of grounding systems used in residential and commercial buildings, which are equipment grounding and system grounding. Equipment grounding connects the metal parts of electrical equipment to the grounding electrode. This helps to ensure that all metal parts of the equipment are at the same potential, which reduces the risk of electrical shock. System grounding connects the neutral conductor of the electrical system to the grounding electrode. This helps to stabilize the voltage of the electrical system and reduce the risk of voltage surges. Proper grounding is essential for the safety of electrical systems. It helps to prevent electrical shock, fire, and equipment damage. If you have any questions about grounding, it is important to consult with a qualified electrician. There are several common misconceptions about GFCIs. One misconception is that GFCIs protect against all types of electrical hazards. GFCIs only protect against ground faults. They do not protect against overloads, short circuits, or other types of electrical hazards. Another misconception is that GFCIs are a substitute for proper grounding. GFCIs are not a substitute for proper grounding. Grounding is essential for the proper operation of GFCIs and for the safety of electrical systems. Another misconception is that GFCIs are maintenance-free. GFCIs should be tested regularly to ensure that they are functioning properly. They should also be replaced if they fail to trip when tested. GFCIs are an important safety device that can help to protect you and your family from electrical shock. However, it is important to understand how GFCIs work and to use them properly. It is also important to have a properly grounded electrical system.